Welcome to Compass, everyone. Today we have Kathleen Jones speaking. She was selected by the Compass Student Committee as an invited speaker, and we're happy to have her today. So now a little bit about Kathleen. So she is a radar scientist at the Jet Propulsion Laboratory in Pasadena, California, and holds an adjunct professorship at the Arctic University of Norway in Tromsø. Her research is focused on using radar remote sensing for studying natural and man-made hazards, and includes development of methods for identifying hazards affecting flood control and water conveyance infrastructure, and for tracking and characterizing oil slicks to help in disaster response and mitigation. She has been the applications lead for the NISAR mission science team since 2015. She received a BS in physics from Texas A&M and a PhD in physics from the California Institute of Technology. And with that, I'll turn over to Kathleen to give us her talk. So thank you.
Thank you very much. I'm going to share my screen and just start right in. Assuming you can see that. So I didn't quite know what to title this talk but I decided that something very generic like musings on what's been happening with L-band SAR for oil spill studies would be a relevant title, because that's what I'm going to be doing, just telling you about the series of experiments that we've done in the past and what we're planning for in the future. So let me see if I can, slides go. So people have known for a long time about oil calming rough sea waters. Seamen have used that since forever, practically. I think the earliest reference that I could find was around 650 AD. And this is a painting from the 1770s showing Dutch seamen using oil to calm waves during a storm on the North Sea. Studying this, I think, started around the time with Benjamin Franklin, when he started doing sort of natural history kind of experiments with oil on water. And there's a nice special issue in Physics Today that talks about some of the work that he did that you can look up online. So how does this work? Well, ocean waves are excited by resonant forcing from the wind, and that's the forcing field, and then gravity is one of the restoring forces, and surface tension and inertia are the other restoring forces. So what happens is that whenever you put oil on water, then the surface tension decreases, and of course the inertia to some extent, depending upon how thick the layer is. And so whereas you might be able to excite a wave with a particular wavelength at a particular wind speed, now that wavelength is reduced. And so the small capillary waves are shifted down to smaller wavelengths, and that tends to damp out the surfaces on the ripples on the surfaces. So here are two videos that I got from Ben Holt, the same sea state in the Gulf of Mexico. And on the right is slicked water, and on the left is clean water. And you can see that, it's much smoother, much less, much more uniform also in the slick. So what happens is that with the ocean surface, with no oil, you have a wave field, and you have a certain dielectric constant. And the seawater has a very high complex dielectric constant, both in the real component and in the imaginary component. So for typical temperatures in the Gulf of Mexico, you would have a value of about 80 for the real component and 70 for the imaginary component. Crude oil, on the other hand, has a very low conductivity. It has a real component of about 2.3 and an imaginary component of about 0. Whenever you have a sheen, a very, very thin layer, then the electromagnetic waves pass through that surface without any modification. The sheen is too thin to really have much of an interaction, and then they scatter from this ocean water below the oil surface. So they see a dielectric that's effectively the same as the seawater, and but they see a wave field that's been damped by the oil. Whenever you start making an emulsion, which is a mixture of oil and seawater, generally that's a thicker layer, and you get a layer. If you have a thick enough layer, then you begin to be sensitive to the dielectric properties. And that dielectric properties of this mixture is a mixture of that dielectric of the seawater and the dielectric of oil. So there's a broad range of dielectric constants that you can get in an emulsion depending upon the fraction of the mixture that is oil and the fraction that's in water. So the bond agreement for oil slick classification gives these codes, that are descriptive, basically based on the appearance of the slicks, and then they relate that to the layer thickness. So a silvery gray sheen will have a thickness that goes up to about 0.3 microns. Rainbow sheen, I think here's a picture over here of rainbow sheen. It goes up to about 5 microns. Metallic, you begin to start looking more uniform, about 5 to 50 microns, and then true oil color goes up from there up to millimeters, centimeters, whatever ultimate thickness. But 5 micron is about the limit for the rainbow and the silvery sheen. So those are very thin layers, and even 50 micron layer is very thin compared to a radar wavelength. And so you don't expect to see the effect of the dielectric until you get into either these true oil color or really continuous true oil color layers, or you get an emulsion that has a high fraction of oil or water. So the thickness where you begin to be sensitive to the dielectric depends a lot on the wavelength. For L-band, which has a 10-inch, 24 centimeters wavelength, then you expect to have a very thick layer of oil before you are sensitive to the dielectric. And for something like X-band, where you have a 3 centimeter wavelength, then of course it can be a lot thinner. So what do you look at whenever you look at the parameters from radar backscatter? I just want to briefly talk about the parameters that I use, because I'm going to be talking about them for the rest of this talk, and so I want you to understand the theory that's behind them. So what I'm looking at is the tilted Bragg model for composite scattering from the ocean surface. It's a composite model. It contains both the influence of the ocean wave spectrum, so the small scale waves, but also the tilt from the background waves. So there's these long wavelength swell waves, and those provide some tilt to the surface, and so that modifies the local incidence angle of the radar. So this is the expression for the radar cross-section for different polarizations, and it depends upon both the ocean wave spectrum and these Bragg coefficients that depend upon this complex dielectric constant. And if you look at the damping ratio, which is the ratio between clean water and just the entire field for the normalized radar cross-section, you'll find that the oil pops out as having a high damping ratio. And that is sensitive to the ocean wave spectrum predominantly, because this term, for the most part, will cancel out between the clean and the slicked water. But whenever you take a ratio for the copolarization ratio of these two, then the wave spectrum essentially drops out. And so if you see a factor for the copolarization ratio, if you see values that are a lot different than the clean water values, then you are seeing effect of the dielectric from the slick. So I'm going to talk, for the rest of the talk, I'm going to focus on these two parameters, the damping ratio and the copolarized ratio. Whenever I look at the data that comes from the UAVSAR airborne radar, which is the radar that I have been using for these studies. So UAVSAR started flying around 2008, collecting data. It's used primarily for studies initially in California, and it was actually designed for doing NISAR studies, so interferometry. But it's a full polarization system, so it can transmit horizontal polarization and receive horizontal polarization, and transmit vertical polarization and receive vertical polarization. Then that means it completely describes the electromagnetic scattering by having these complete orthogonal components for the polarization of the radiation. In addition, being an airborne instrument, it's got a very low noise floor. So a lot more of the transmitted power is reflected back than you would get with a spaceborne instrument, simply because the subtended angle for the receiver is so much larger whenever it's closer to the ground. So you get a much higher contrast for oil spill studies than you would for an instrument operating from space. And that is shown here in the oil slicks that were seen in Barataria Bay during the Deepwater Horizon spill. Here they are shown from a UAVSAR image, and you can definitely see those slicks quite well. The oil spill studies that I've done have been in the Gulf of Mexico, off of Louisiana, in the North Sea, off of the southern coast of Norway, and we're just starting to look at working in Santa Barbara, where there are seep fields off the coast of California. So we started using UAVSAR during the Deepwater Horizon spill, and that occurred, there was a fire on the rig on April 21st, 2010. And as you know, something like, I forget how many, 8 billion gallons of oil were spilled. I'm not sure of the exact number, but it was an enormous amount of oil that was spilled during that time. And before that, the Deepwater Horizon SAR was widely assumed to be only useful for detecting oil slicks. And by that, I mean a binary, here's a slick, here's clean water. It's a binary value. And the assumption was that only kind of these short wavelength instruments, C-band, X-band, were assumed to be capable of that because of the damping of these short scale capillary waves. And so whenever we planned this campaign for UAVSAR, you can see here all of these flight lines, these blue flight lines. We really concentrated on the coast because we thought that what we were going to be doing was looking for oil impact. We would measure this area, predominantly clean. We come back after oiling has occurred, and we do ecosystem studies. But, you know, we decided we would image the slick anyway, even though it didn't seem like we could expect to get much from that. So by the time we got funding and approval and everything done, it was two months after the oil spill occurred. We went out on June 22nd and 23rd. We took off from California at dawn. This is us getting on the plane at dawn. We flew to Louisiana. We started doing these flights. We refueled in Pensacola, took off, came along the coast, landed in New Orleans, and did these lines over the main slick the second day. And then we ended up, you know, flying over all the way to Corpus Christi along the coast. It was incredible. It was 21 flight hours, 3 flights, so 7-hour flights on these planes. It was phenomenal. thing to be doing. It's very high energy. It was a lot of fun. But whenever we got the image, you could really see the Deepwater Horizon oil slick, the main slick in the image. And whenever you looked at it in more detail, not only could you do this differentiation, but if you look at the blue here being the intensity for the clean water, and you could definitely see a lot of features within the slick. So we got photos that were being taken by the Aspect aircraft from EPA, and we correlated the features in the scenes with photographs that had been taken at around the same time, and pointed out that, you know, we see these emulsion stringers in the field. We see Langmuir circulation cells that show up in these photographs here. We see the trail of a boat here, shown here. We see high density of oil at this location close to the Deepwater Horizon rig site here. And so there was a whole lot of things that indicated that not only could you detect oil with L-band, but you could also, to some extent, characterize the oil within the slick. And so I had a intern, Brent Minshew, here at JPL for the summer, and he wanted to do something other than clean out the lab. So I thought that it would be really nice if he worked on this data set. And so we worked with Ben Holt and analyzed the data set from that. And what we found was that there was a big difference between clean water, which is shown here in dark blue, and the oil within the slick. And there were differences depending upon where in the slick you were at. And in fact, in this particular line here, you could see where you went through an area where the oil had been burned, and, you know, it went back up, the cross-section went back up to that of clean water. So we were definitely seeing signatures from the slick and differences. So did modeling and used the dielectric of a mixture and showed that these variations that we were getting for this copol ratio could be related to the emulsification factor of the oil within the slick. And that was really, really groundbreaking, I think, to actually do this kind of derivation from the data. From L-band data in particular. So we began to do more work trying to do more oil spill studies with UAVSAR. And of course, you know, can't always find a nice spill, and you certainly can't plan on a spill in general. So the Norwegians just happen to do an oil on water spill exercise almost every year, where they go out in the North Sea and they dump a bunch of oil, and you know, then they test their equipment for picking up the oil. They measure the efficiency, they develop new technologies, or I should say they fund development of new technologies, and they test them during these exercises, and they train personnel. And this is funded by the operating oil companies through this organization called the Norwegian Clean Seas Association for Operating Companies, or more often called NOFO. So we collaborated with Camilla Brecke at University of Tromsø and got invited to participate in the 2015 exercise. So we went there with UAVSAR. There was a coordination between the NOFO and the University of Tromsø on releasing some amount of oil that, instead of remediating, they just left it to evolve on the surface. And they also made different emulsions with a range of oil to water ratios. So they made one emulsion that was 80% oil, one that was 60% oil, and one that was 40% oil, so that we could look at the difference between those emulsions. And they also released at the same time this biogenic slick simulant, which was kind of a lubricant that's used in added to drilling fluid. And it's water-based, and they used it as a simulant for the plant oil. I think the closest thing it relates to is something like olive oil. I was told by a chemist. I'm not a chemist. So went out and dumped about 3 barrels of each of these emulsions and this plant oil simulant in the sea. We separated them by something like 1 nautical mile, and then UAVSAR took off and started doing circles over the releases and imaging the release points from different, basically from different viewing angles. And of course, after, and we flew back, we actually took off in the morning. We went over, we flew back, we refueled, and then we came back in the afternoon and imaged it some more. Now, with 3 barrels of oil, 0.5 cubic meters, you're not going to get a really thick slick. So these were actually sheens, and very shortly after release, we were only there for the release of the 80% emulsion, which was released last, and very rapidly it had expanded. I think after the second flight, it had expanded to the point where it was less than 1 micron thick. So somewhere around 1 micron, 0.8 micron thick for these slicks. So at the time, of course, this is in the North Sea, and wind was a factor. For very low wind, you don't get enough contrast between the clean oil and the slick. So up to about 3 knots, you're not going to be able to get contrast between the slick and the clean water. Then you have different wind speeds where you can image the slick, but at some point the wind becomes so high that the breaking waves tend to mix the oil down below the surface at very high wind. And this limit is around something like 12 to 14 meters per second. And so what we had during this exercise was wind speeds that were 9 to 12 meters per second. So kind of at the high end of what you would expect to be able to see the slicks. This is photographs of the release of the 60-40 ratio. You can see this is the 80-20 ratio. You can see some white capping. You can see the slick here with even white capping in the area of the slick. So we were definitely in this in the regime where you would expect the slicks, oil in the slick, to be mixed down below the surface. So we also released these drifters simultaneously with the release of the plant oil and the 80% emulsion. We released one drifter that was called an I-sphere drifter. It sits mainly above the surface, and so it drifts with the wind. And then we released one of these submerged marker buoy, and that moves more with the currents. So I think these two, the red and the blue, show the path of the I-sphere drifters, so the wind-driven mainly, and then these yellow and green show the path of the 2 different submerged buoys that are drifting more with the currents. And that was done so that whenever we did models, comparing a model with the evolution that we measure of these slicks, then we would have local currents to put into the model. So this is how the slicks evolved in shape and in damping. We go from 5:30 a.m. up to 1:20 p.m. With a break at this point around 9 a.m. when we flew back and refueled and came back out. And the slicks, this is a plant oil at the bottom, then the 40% emulsion, 60% emulsion, and the 80% emulsion. And then you can see how they evolve with time. And if you just look at the three mineral oil emulsions, then they pretty much do what you would expect. They expand, they spread along the wind direction. This is the wind direction. And the 40% oil emulsion damps, disappears from the surface much more quickly than the 80% oil. If you look at the plant oil, plant oil should not be able to form a slick at 12 meters per second. So, what's going on with this? You see that initially it spreads in the direction of the wind, but after that, it just appears to become more and more of a circular blob, and it persists on the surface. How did this happen? This is not what one would have predicted would happen at a 12 meter per second wind. So the people from, I'm sorry, I'm gonna have a little water here. So Knut Frode Dagstad and Johannes Roers and Øyvind Breivik from Met Norway, they used their open oil model and initiated with the data that we had in order to model slick transport. And they adjusted the droplet size, the oil droplet size, and the entrainment rate below the surface in order to match the data that we measured. For horizontal movement, they had the ambient currents from the drifters. They also compared it to a model, but the results from the drifters were much more accurate. They used Stokes drift, windage, horizontal spreading on the surface from the wind, vertical motion. You had entrainment by the breaking waves, you had diffusion, and you had buoyant forces, which caused the oil droplets to rise back to the surface. And if you looked at what happened to the surface component, what we measured with the radar was, of course, the surface component only. These different colors show the way that the slick evolved with time. This gap is when we went back to refuel. And this is the plant oil, more circular in the end. And then this is the shape of the oil emulsion. It started out like this. There's a gap, and it spread with time, and it also moved with the currents, just much like the motion of the plant oil. So this origin point kind of moved in the same way. So they tuned their models so that they matched this, and they found that they got very good agreement. If this plant oil simulant had droplet sizes that were 1/5 of the droplet size of the oil emulsion, and that entrained much more rapidly than the oil emulsion droplets. So what was I thought was most interesting was what happened below the surface. So if you looked at the submerged component of this slick, then for the biogenic slick, if you started the simulation at the time of the release at 5:48, that's the time that we took our first image, then by 6 o'clock, 23% of the biogenic oil was below the surface. By 8:30, 23% was left at the surface. And very shortly thereafter, most of it was below the surface. So most of it moved below the surface. The mineral oil, on the other hand, by 6 o'clock, you had 71% still at the surface. And even later, you had roughly 50% stayed at the surface, remained at the surface. So the biogenic oil mixed below the surface much more quickly And that became a reservoir for resurfacing oil. And that's why this slick tended to remain on the surface, because there was a reservoir of resurfacing oil that renewed it over time. So that was very interesting and helped to develop these models. The other thing I want to show from the comparison between data that we acquired in the Gulf of Mexico in 2015 with the data we acquired in the North Sea in 2015 is the damping ratio here. This is a damping ratio, and you can see a lot of structure. This is the first image of the slick for the 80% oil after initial release, so it still hadn't formed a relatively uniform sheen layer at that point. But the copole ratio shows essentially no signature. So we definitely don't see anything from the dielectric of the oil in that case. And in the Gulf of Mexico, there is a small signature, but not nearly as well contrasted as you get with the damping ratio. So the damping ratio is definitely a much better measure to use for inferring the thickness of the oil. However, once you get to a very thick layer, you can get information from the copolarization ratio. So the third experiment that we did was in the Gulf of Mexico, Mississippi Canyon Block 20 in November of 2016. There, it was a huge campaign funded by Bessie. NOAA was heavily involved. Oscar Garcia, now with water mapping, brought his thickness measurements, and there was a boat crew that went out collecting samples. A lot of work was done with different sensors, and NASA funded UAVSAR to participate. So Bessie funded all these other activities, and NASA funded UAVSAR to go out and observe this also. So this is the slick that we imaged at that time. This is the slick from Origin's point is the Taylor Energy rig, destroyed rig. It's been a site in the Gulf of Mexico since, I think, 2004 or 2006. And, you know, a very substantial slick is formed from that particular site. For reference, I said that there was a boat crew out. If you have very good eyes, you can see a little bright spot at this point. That is where the boat crew was, at the very close to the origin point for this slick. So what we observed was that there was a lot of variations in the intensity within that slick, indicating that there was a signature for thickness or emulsification from the data that we had. And I just want to show the damping ratio. This is a zoom in to this particular area of the slick here, not exactly at the origin point, but it's in an area where we saw a lot of variation. So this is the damping ratio, and this is how the damping ratio evolved. Each of these scenes is 30 minutes apart. So we acquired something like 11 scenes, 30 minutes apart. And you can definitely see the accumulation of oil, the apparent accumulation as measured by this damping ratio along the edges of these fronts within the slick. So that was very interesting. We also did a comparison between the C-band satellite data from RadarSat-2 and the L-band data from UAVSAR. The C-band data from RadarSat was acquired in quad pole mode with a very low noise floor. I think it was minus 35 dB. And UAVSAR had a very low noise floor, also something like -45 dB. So both of these had good contrast between the clean water and the slick, and a lot of capability for measuring thickness variations within the slick. So with the RadarSat and with UAVSAR, this is RadarSat parameters, the entropy and the damping ratio. And this is UAVSAR measurements for entropy and damping ratio taken at the same time and over the same area. And in an area where we had spotters that had observed a mat of sort of dark red-brown emulsion within the slick. So this area was known to be red-brown emulsion, very thick oil. And if you look at the entropy for RadarSat versus the damping ratio for RadarSat, then what we concluded was that the damping ratio is better than the entropy at determining oil thickness, relative oil thickness signatures within the slick. If you look at the difference between UAVSAR, L-band, entropy, and damping ratio, you see the same thing. Damping ratio is better. This is useful information because the entropy requires 4 polarizations. That's a much more complicated instrument than something like a damping ratio measurement, which is a single polarization parameter. So it's much easier to get measurements, a radar instrument that can measure in a single polarization than in all 4 polarizations. Also, though, you can see that comparatively, C-band is much better than L-band for identifying where the thicker oil patches are. So the conclusion was that the VV damping ratio is a reasonable proxy for relative thickness for either C-band or L-band, but that you have to have a low noise instrument for this to work. We also took that sequence of images for UAVSAR, so the sequence of images that were acquired at 30 minutes apart. And my student in Norway, Martina Espeseth, used it to look at how to derive some products that could guide responders. So the idea was to come up with parameters that could be used to easily show where the thickest oil is, where it's most likely to be in the future, and to detect the drift pattern of the thicker oil. Now, if you recall that sequence of images, where the thickest oil went was more driven by collection along these fronts than by the wind or by the currents alone. So you can't really just use wind or current to tell where the thicker oil is going to be. So there were 2 methods that she used, one for detecting the areas that consistently have oil that is above a particular damping ratio. And this is an example of that product. This would tell somebody who had to respond that if they went to this location, they're most likely to find oil there, the thicker oil there. And recall that the boat was down here, so they were not in the best location for finding the thickest oil, unfortunately. And then the second method detects the drift pattern for the thicker oil, and it kind of shows blue is areas where the thicker oil is moving out of, and red is areas where the thicker oil is moving into. I give this reference here so that you can get some more information about how those methods work. They're actually extremely general. They could be applied to optical data, any kind of data, in order to look at this kind of information. So what's next? So next is that we're going to start looking at these oil fields, seep field off of Santa Barbara in California. And that's in a project that was funded through the NASA Applied Science Disasters Program. It's led by Frank Minaldo from NOAA, and JPL has co-eyes, me and Ben Holt. It also has collaboration from the University of Tromsø, from MDA, the organization providing RADARSAT-2 data, and Oscar Garcia at Water Mapping for working on the in situ measurements. And the goal is to develop methods for calibrating the radar against the oil thickness in order to create an operational oil thickness product that NOAA would be able to generate just automatically. So our first plan was to go out to this Taylor Energy SEEP in the Gulf of Mexico in 2019, and then to participate in the NOFO oil and water exercise in 2020. So that Taylor Energy SEEP was capped back in 2019. So that kind of got rid of that particular source of oil. So we didn't have it to go to anymore. So plan B was to go to Santa Barbara. And then that was delayed because of instrument issues. And then to go to NOFO in the North Sea this coming year. And of course, then COVID strikes. And so we go to plan C. Now we're going to go to Santa Barbara in probably March of next year, and then do the oil and water exercise in either 2021 or 2022. The Norwegians have not decided yet whether they're going to have a 2021 exercise simply because of the uncertainties with COVID. But on the positive side, we now have funding also to do imaging over the Olmsted oil spill test tank in New Jersey. So it's going to be what we do next. So I have a few minutes. I'll just show a few slides more. This is the coast off of Santa Barbara. It has some very nice lookalikes. These are kelp beds that are consistently along the coast. And then the coal oil point seep field is out here off the coast. And that's a reliable source of mineral oil. This shows a boat and kind of what the oil looks like. Ben Holt has been out both at the Taylor site and in this particular seep site. And he said that the oil there is actually quite different, that it'll be very interesting to look at images from this site, which has both different characteristics of the oil. And this shows Oscar Garcia with his drone out last year, 2018, 2 years ago, at the seep field, and he'll be returning with that also. So in the future, the next thing on in terms of L-band instruments that's coming up is UAVSAR will continue flying in the future, but also we'll have the NISAR mission coming online, which NISAR is going to carry L and S-band instruments. So NISAR is the NASA-ISRO SAR mission. It's a collaboration between NASA and the Indian Space Research Organization. NASA provides the L-band SAR. ISRO provides the S-band SAR. The L-band SAR is used for near global land imaging. It will have dual pole operation over land. And the S-band SAR will be mainly imaging India's areas of interest, which is Southeast Asia and Antarctica and some of the North polar ice fields, but certainly not everywhere. We're trying to get both L and S-band SAR data over oil spills as emergency response, simply because both the two look at different parts of the ocean wave spectra, so you really can see different things with those two instruments. So the instrument is designed for doing a broad range of science, solid earth science. It's designed for interferometry, for cryosphere, looking at ice sheets and glaciers, for ecosystems, looking at forests, looking at disturbance, looking at wetlands, a lot of work on agriculture, and also looking at permafrost and how permafrost is changing. For the applications, it is going to provide data for urgent response. Of course, all of this data is also of interest for applications. If you're going to study the mechanisms driving earthquakes, you can use exactly the same data to understand the risk from earthquakes. You can take the same data that you acquire for agriculture to do monitoring, operational monitoring, those kinds of things. So the two, what's happening is that we're trying to meld science and applications together so that more and more of this data that NASA acquires for science is also used by the applications community. So just a few things. First of all, you're probably wondering when it's going to launch, and it was supposed to launch in 2022, the beginning of 2022, but it looks like because of the delays from COVID, it's going to launch in January or February of 2023 now. One, it's going to have a new imaging mode called UAVSAR that allows you to have 240 kilometer swaths for regardless of the polarization mode. So it's going to have dual polarized acquisitions at 240 kilometer swath width, which is really great. It will have a 12-day orbital repeat cycle, which means that any point on the land will have between 2 and 5 overpasses. Depending upon the latitude, you'll get more orbit overlap at high latitude, so you'll get more passes during that 12-day period. They won't be from exactly the same imaging geometry, but they do image the surface more often. And then data will be acquired on every orbit, ascending and descending. It's a left-looking instrument. Most of the instruments that are operational now and all of the commercially available data, SAR data, are right-looking instruments, and the implication from that is that you get better coverage at the North Pole than you do at the South Pole. So NISAR will turn that around. Left pointing, you'll get much better coverage at the Antarctic than you do in the Arctic. That's not so great for Arctic sea ice, but since the other sensors measure the Arctic better, the idea is that this will be an opportunity to get much better data over Antarctic, especially the land mass in the Antarctic. So I just want to show how UAVSAR works a little bit because it's pretty cool. So on transmit, all of the TR modules, transmit receive modules, that's red here, it flashed red. That is the pulse going out, but the return echo is received, so it sweeps through the TR modules, receiving different parts from different parts of the ground on the different transmit receive modules. So at some point in time, it can be receiving from 2 different echoes simultaneously. The implications, though, is you have to do beamforming on the satellite. And so that means the onboard processing is not reversible. So it's a pretty complicated system. But on the other hand, for scientists, if you get a 240 kilometer swath, that is great. So I just want to have my last slide, next to last slide, showing you a picture of this 12-meter diameter reflector for NISAR. That's pretty impressive. the size of this. Here's a person at the back very close, so you can really see the scale of this reflector. So in summary, I just want to say that for SAR remote sensing, I think the key parameters that people need for response are position, extent, where the oil is going to go, where the oil came from, the thickness, and therefore combining it with the extent, get the volume, emulsification, because that has implications for how long the particular material will be able to remain on the surface, and then oil type, whether it's a mineral oil or a biogenic oil. So SAR does slick position and extent extremely well already. Forecast models, transport models are good, and they can be used somewhat for hindcasting, and their capability is really improving. I think that the thickness and volume, the emulsification for the oil to water water fraction and the type, those are capabilities that are subject to continuing research. So there's a lot of work that's left to be done. So that's the end, and I'll take questions if there's time. I hope I haven't run out of time yet.
Thank you, Kathleen, for that interesting talk. Excellent. If anyone has any questions, please turn on your camera when you speak. It helps us know who we're talking to when we're answering questions. So does anyone want to go first?
Ask a question.
Yes.
Very nice talk. Thank you very much for giving this great seminar for us. I have one question, well, two questions. One is, how long does it take to post-process this aircraft or even satellite? I mean, is it like close to real time, or it takes months?
It does not take months. Usually we get, since the aircraft, the data is stored on a disk on the aircraft, you have to get the disks back to JPL to be processed. We actually have an onboard processor. So on board, we can get some images, but we don't get the quality of these images. That is in near real time. I think it lags the acquisitions by a few seconds.
Okay.
So you could get a pretty poor quality product to the ground from the aircraft. It does show some of this contrast, but not the as good as you can do afterwards. For the satellites, I think that they now can do the processing within a day very quickly for this data set that was acquired in 2016.
And my second question was, what's the area that you can cover with this aircraft typically? I mean, you have,
yeah, it's a 22-kilometer swath, and so and it flies at 200 meters per second, so you can cover a lot of area pretty fast.
Okay, thank you.
May I ask a question? Kathleen, that's fantastic work. It's so comprehensive research. I was working with Tamai project in Splash in the Gulf of Mexico near that damaged Taylor's platform. And we took some number of images with German Aerospace Center, with Susanna Lehner, with Will Perry from Canada. Yeah, that was fantastic information, very useful. Was most important to interpret it somehow with in situ observations which were provided by the CARS consortium. But my question is, you have simultaneous measurements of SAR satellites and airborne satellite. What's your opinion about advantages, disadvantages of both? Yeah, it would be great to understand which is to use in what situation.
Yeah, so most of the satellites data, for example, Sentinel or even NISAR, is going to have a pretty high noise floor. And so being able to measure the thickness or the volume is going to be very hard with those instruments. You can still do detection, sort of binary with those instruments, but not a great job of anything else. RadarSat-2 in this particular mode, the quad pole mode, which is not the standard one that's acquired with, is quite good. We showed you an example there. It is its noise floor is minus 35 dB. That's 10 dB, possibly more, below most of the bigger SAR satellites operating from space. So it's a huge difference. None of them compete with these airborne sensors, though. I mean, the spatial resolution you can get from the airborne sensor combined with the noise floor is really excellent. But, you know, it's an aircraft. It's great because you can target where you want to go. You can repeat these images like I did very quickly in order to develop up the set you need for forecasting, but you have to get the plane there. So they each have their advantages and disadvantages. I'd say the advantages of satellite is for monitoring, and the advantages of the aircraft are for response.
Thank you.
I would also like to thank you for a very informative talk. I learned a lot today. My question is, I'm a little naive to this, is how much does one to use this plane? How much does it cost per day?
Very frequent question. It's $3,000 per flight hour. So whenever I was talking about, you know, the 21 flight hours during the Deepwater Horizon, you know, 65,000.
Okay. It's not totally out of the ballpark, you know, relative to using a large ship for the day. It's, you know, it's within a factor of 2 or so. So, okay. Yeah. Thank you.
Sorry. Go ahead, ask questions.
Does anyone else have any questions? Well, well, if no one else has any questions, thank you, Kathleen. That was a great talk, and we appreciate you taking the time to give the seminar to us at Rasmus. So
I was glad to do it. It was a lot of fun. Thank you.